All right, guys, welcome back. So what we'll do here in the second hour is we'll just do a very brief kind of intro to sorting and kind of some of what the way the different sorting algorithms work. I meant to get a deck of cards for this one, but I forgot. Actually, I'll link to a video that I did last semester that kind of showed this whole deck of cards philosophy of how to do different sorting stuff. So it's just kind of like a brief overview of how this sorting, the time complexity of them and how some of the different sorting algorithms work. Okay, so the idea of why we even study sorting in the first place, and again, you'll do this in much more detail in future coursework, but the idea is that sorting algorithms provide us a very good, simple way to kind of approach problem solving in general. Remember, one of the big things that I really want you guys to understand is that computer programming, computer engineering, quite frankly, engineering at all, is not about memorizing a bunch of correct answers to the questions that we face, but it is about being able to analyze and understand a problem and be able to develop a solution. Okay, and sorting algorithms allow us to be able to understand what the problem is. We have a mixture of stuff that's not sorted, and we want to be able to put it in an order of some kind, right? And there's lots of different ways to do that, right? As we're going to learn here today a little bit. And so there's not one right solution. Some are faster than others, and even within the ones that are faster than others, it oftentimes depends on what the starting point is, right? Is the starting data set generally sorted with just maybe a few items that are out of place? Okay, well, then a certain sorting algorithm that would generally be faster in a completely mixed up starting point might not be so fast in that type of situation. Okay, but it can also allow us to be able to do some good practicing fundamentals of being able to understand techniques like if statements, loops, writing methods, understanding arrays, array lists, those kinds of things. Okay. And we can also use them as great examples to understand algorithm performance. And again, this class is not the algorithms class, and so we're not necessarily trying to get deep into understanding algorithm performance, but it is a reason why you might want to understand sorting. Okay. All right. So generally, when we start talking about sorting, we kind of go with some general what type of data to sort, that kind of stuff. And so what we'll do is we'll say, okay, let's just go integers. You can do other data types. When we sort things, we could do other data types. It could be strings, it could be doubles, it could be all kinds of possible data values. Right? It could be dates. Right? But when we study sorting, usually we just go ahead and say, let's use integers because numbers, we know those, right? Numbers are easy. And then when we get to a data set, a data array is going to be ascending. So low values first, high values last, right? And then we can use the programs that we deal with. Hold on a moment. Okay, excuse me. So what I was saying was this, once we understand that the data are stored in an array of some kind, the arrays provide very good ways to be able to manipulate the positions of our data items, right? You know from our discussions in previous about the data structures like linked list and array list that it's harder to swap two items in an array list or a linked list. Much easier to do that in an array. All right. So then we can easily just modify our programs that we write, our different sorting programs, to be able to use different types of data, or even say instead of doing ascending order, we do descending order, that kind of thing. All right, let's move on. So insertion sort, the idea is we grow from our array from the first item, then we include the second, then we include the third, and then the fourth, and so forth, and whatever item we're currently working with. So when we're working to the fourth item, for example, we want to put it into our array at the position that it should be in order to maintain that the first K items are sorted. Okay, so basically let me show you what I mean here. You have this value, okay, we're starting on the first value, 2. Okay. It's an array of 1. An array of 1 is sorted. We're done, right? So now we say, okay, now we're going to include this second item. Well, now we have an array of 2 items. 2, 9 is sorted, right? Because 9 is greater than 2. So now we're going to move on to the third item, 5. Now 5 is greater than 9, so we don't need to keep it here. We need to swap these two, right? So 9 needs to move into this position. 5 can move here. Is 5 greater than 2? Yes. So we don't need to move anymore. So now we have 2, 5, 9. Now we're going to add 4. Now 4 should go before 5. So what we're going to do is we're going to move 9 over, we're going to move 5 over, and we're going to insert 4 into here, into this position. We do this again with 8 by moving 9 over. 1, oh, it's going to have to go all the way at the beginning. So this needs to move here, 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 and 1 comes at the front. Okay, and then finally we're going to put 6 into position where it should go, which would mean here between 5 and 8. We're going to push these 2 along. If you think of it like a deck of cards, what this is like you're saying, okay, I have a few cards here actually. Here, my son left just a few cards here. Okay. So here are my cards. Let me see what my screen looks like. Okay, so here are my cards, right? It's kind of these are my cards. Oh, one of them's backwards. All right. And the idea here is what I'm going to do is I'm going to just take my stack of cards. They're all just shuffled, okay? And what I'm going to do is I'm just going to take the first one. Okay. I'm going to take the first one. It's a 3. Okay. And then right, and then I'm just going to take the second one, which is a 5, and I'm just going to put it into position where it should be, behind the 3. And the third one is actually another 5. Let me unblur my background here. How do I? Because I think blurring the background keeps messing up the shot here. All right, so then another 5, and then I'm just going to put that behind the others. Okay? And then I'm going to have a queen. Okay, so this is generally sorted, isn't it? So I'm just going to put it behind the others. Now I have a 6. and I'm going to insert it where it belongs. Did I do that right? Yep. Okay, good. Inserted it where it belongs. And then the last one is a 5. So I'm going to insert it where it belongs. That's why it's called insertion sort, is because what I'm doing is I'm inserting the mass value I've gotten, and I'm inserting it into the place where it goes. Okay, I didn't realize when I saw all those cards here, I didn't realize there were so many 5s in there. So it's going to be kind of strange there. All right. Right, exactly. Well, you don't have to check every value, Regep. What you just need to say, okay, so basically the way that insertion sort works, in this example where I just did this, was we have, let me go back a couple of steps here, where I had, let's say I had this, right, the 3, 5, 5, 3, 5, 5 queen, okay? And the next card I get is a 6, and the way that insertion sort itself works, so it's based on this idea of inserting it into the place where it goes, but what it actually does is it says, okay, just compare these two. Is this greater than this? No, so move this one back. Is this, now we've got it like this. Is this greater than this? Yes, so we leave it there. Okay. Then we do that again here, okay. Is 5 greater than queen? No, so we move it to here. Is 5 greater than 6? Yes, so we move it to here. Is 5 greater than 5? No, so we leave it where it is. Okay, so that's kind of how, that's why we don't have to compare it to all the previous values. We just only have to compare it to the next one up each time. Okay. Right, yeah, exactly. Right, and so you can imagine that, let's say we wanted to sort these lowest to highest, or I guess you're looking at it like this. Well, this is how I hold my hand when I play cards. Okay, so we want to sort them lowest to highest, right? And so if we started with an array that was the opposite, that was highest to lowest, then there would be a lot of swaps that would be necessary, wouldn't there? Right? There would be a lot of swaps that would be necessary. Okay, so an insertion sort would be a very slow algorithm for an array that's initially sorted the opposite of how we want it to be. Okay, I think I'm gonna have to go check the door again. One moment. Oh, the joys of the pandemic online teaching. Okay, so let's move on. All right, so that was insertion sort. Again, there's an animation that's available if you want to look at it, right? So here we compare 2 to 9, we compare 5 to 9 and swap them if necessary. 4, we're going to move 2 items, over, and so forth, right? So this was our example here. Okay. So here again, if we were on 4, save 4 to a temporary variable. We move everything that's greater than 4 over 1 position to the right, and then we put 4 into the open position once we get to something that's less than or equal to it. Okay. Right. So this is how we might go from this pseudo code, right? That for our int I is 1 to the list.length, so for every item in the array after the first one, we're going to insert the list that's at the current index we're looking at into the sorted sublist of 0 I minus 1. So when I becomes 5, for example, we assume that the list from 0 to 4 is already sorted. We've already done the work of sorting that sublist, So we're just putting the thing at index 5 into the correct position inside of that sublist. And now at the end of this time through the loop, we have a sorted sublist of 0 up to I. And once I becomes, right, the n minus 1, the length minus 1, we have an entire sorted list. Okay. So if we want to push that into Java code, it might look something like this. Not the only way that we can write this. We could do this lots of different ways, but this would be one way to do this. We're taking this pseudo code here and we are making it into we're making it into this Java code here. So we just take this Java code and put it into that pseudo code location. And that's how you would do insertion sort. Okay. Insertion sort, because in worst case scenario, we will have to move, like let's take the last item. Where was it? This one here, when we were working on the value 1, how many items did we have to move? Well, we had to move 1, 2, 3, 4, 5. We had to move all of the items that were before this, right? So the idea being here, we could have to do every time through I minus 1 moves before we can put this thing at index I into the correct place. So this is why insertion sort's considered a big O of n squared algorithm. We have to do that for n items, all right, for all items in the list. All right. Bubble sort's another example of an n squared algorithm for sorting. This time the idea is that we're instead of having a sorted sublist, right, a sorted sublist, and we're taking a value and inserting it into a position, what we're doing is we're trying to say, okay, so like in this version of the bubble sort, we're going to end up with the greatest value in our array in the last position after the first pass through. Okay, so here what we do is we compare 2 to 9. Is 9 greater than 2? Yes, we leave it there. Then we compare 9 and 5. Is 5 greater than 9? No, we swap them. Now we compare 9 and 4. Is 4 greater than 9? No, so we swap them. Is 8 greater than 9? No, so we swap them. Is 1 greater than 9? No, so we swap them again. And when we end up with that first pass through, what we end up with is the greatest value in our array is now in the last position. Then we just do the same thing again with these n minus 1 values. Is 2 greater than 5? Sorry, let me do it the same way I did for this first set. Is 5 greater than 2? Yes, so we leave them alone. Is 4 greater than 5? No, so we swap them. Is 8 greater than 5? Yes, so we leave them alone. Notice that 5 and 8 here, 5 and 8 here. Is 1 greater than 8? No, so we swap them, and now we end up with the second largest value here in the second to last position. And we don't need to compare these last two values to see which one is greater, do we? Because when we did the first pass through, we ended up with the largest value here in the last position. So now in the second pass through, we know that this will be the largest value of this subset, but we know that it cannot be greater than the thing in the last position. All right. I hope that's clear why that is the way that it is. So then we keep doing that over and over again. So then we do it for this 2, 4, 5, 1, and we end up with 5 here. Then we do it for 2, 4, 1, and we end up with the 4 here. And then we do it for 2 and 1, and we end up with this sorted array. And what we did was we simply said, I want the largest value here. I want the second largest value here, third largest here, fourth largest here, and so forth all the way down. Okay. And we call this bubble sort because it's kind of like the largest value is bubbling up, like if you ever drink Sprite or Fanta or Cola or Guzzles or anything like that, you know, bubbles like come up and rise to the surface, right? And that's what's happening with the largest value here, is it's bubbling up through, like it doesn't just, the bubble doesn't just miraculously go from somewhere low in the cup and just suddenly appear up at the top of the liquid, right? What happens? It goes up, it flows up, right? And that's what's happening with this largest value, is it's moving its way through up to here. Okay, it's moving its way through up to here. So that's why we call this bubble sort. Again, because we're visiting every value once, and we're every time through, we're going through the list the entire time looking for the largest value, and we could end up with as many as n swaps. Again, if the largest value, if this array was generally sorted in descending order, like let's say it were the exact opposite of this one, so 9, 8, 5, 4, 2, 1, we would have to swap everywhere along the way. You know, just swap, 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 swap. All right, so in the worst case, we might have to do n minus 1 swaps, and we might have to do that n times. Right, so we end up with this n squared algorithm. Okay, again, this bubble sort animation will help you understand also in a visual way of how these things can work. All right. Okay. Merge sort is one of our quicker sorting algorithms. We call this n log n. Okay. And this is what's considered a divide and conquer algorithm. And divide and conquer is based on the idea that if you have an army of 1,000 people that you're fighting against, it'd be a lot easier to fight against two armies of 500 people and defeat the 500 first and then fight the other 500 next, right? That's kind of the idea of the divide and conquer, is we take the problem, we split it into as equal as possible parts, okay, and then solve the parts. Right. Now here the idea is we take this 8-value array, we split it into 2 4-value arrays, and what we're going to do is then we're going to sort these 4-value arrays. We're going to sort these 4-value arrays, right, and then merge them back together. Okay. And the way that we sort these 4-value arrays is we do it again. We split them again. We divide again into 2-value arrays. And we might even go as low as a 1-value array. Now, once we end up with the 1 value, this is a sorted array. We're done, right? So then when we merge them together, we merge 2 and 9 together into an array of 2, 9. Notice that sometimes we end up with the same thing we started with, and that's okay. There's no problem with that. All right. And then I'm just going to go on this side for this one because there's not really enough time to go into details on merge sort. But the way we would merge this 2 and 9 and 4 and 5 is we use the fact that both of these are sorted already. Okay. So then we look at the lowest value here and the lowest value here. Well, which one's less? Well, this one, 2. So we move 2 into the first position. Then we move to the next one on this array, but we stay in the first position on this array. Is 9 less than or greater than 4? Well, it's greater than 4. So we want this value next. So 4 comes into this position. Now to fill that third position, we compare this one with this one. 5 is less, so we move it into its position. Now we're done with this array. We can just toss it and just give us the rest of these values here. 9 goes into that position. And we just do that again here. We compare the first 2 values. 1 is less, so it goes first. Then we compare 6 and 2. 2 is less, so it comes next. 4 and 6. 4 is less, so it comes next. 5 and 6. 5 is less, so it comes next. 9 and 6. 6 is less, so it comes next. 9 and 7. 7 is less, so it comes next. 9 and 8. 8 is less, so it comes next. Now we're done with this array. and this one can come over here. Okay. Now, one thing that I do want to talk about the merge sort is it is a much faster algorithm because it's considered divide and conquer here. So what we'll see here in the time required, it ends up being called, instead of n squared, it's considered n log n. That doesn't mean that it's free in the same way that the other ones were. And what I mean by that is because of the way that merge sort works, we must use an additional array to store the values as we put them in here. So as we have these two subarrays and we're going to merge them together, right? We're going to merge them into a third array. So it takes up each iteration through, it's going to take up twice as much space in order to keep that in order to keep the things in sorted order. Okay, so it takes up a lot less time, but it's also going to take up more space. Both bubble sort and insertion sort, and then there's another one we didn't talk about here today called selection sort. Those are all n squared algorithms, but they also all use the array as is and just swap values around. So it's like this deck of cards. It just we don't have another set of deck of cards or anything to hold on to them, right? We just move cards around. Okay. That's how those other n squared algorithms work. So space isn't a problem with an n squared algorithm, but with merge sort here, it can be a problem because the space becomes an issue. Okay? It's a lot faster, but space it can take up. All right. Again, merge sort, we call this an n log n algorithm. Okay. Quick sort is another example of a divide and conquer algorithm. Quick sort, the idea is we have what we call a pivot value. Okay, and what the idea is that you choose a pivot, let's say 5, and then what happens is you work to have everything to the left of the pivot value be less than the pivot value. So 5 is, we just choose, let's say we choose the first value in the array, and that's going to be our pivot value. And then what we do is we make sure that everything to the right side of the array is going to be greater than our pivot value. So notice here, before this 5 and 4 get swapped, right? Everything to the right of the array is greater than 5. Everything to the left of that spot is less than 5. So then we're going to sort this set. All right, and we're going to sort this set in the same way separately. So here now to sort 4, 2, 1, 3, 0, we choose the first item in our array, and that's a pivot. That's our pivot. So now what we're going to do is we're going to make sure that everything to the left, right, everything to the left is going to be less than 4. Everything to the right. Well, this one was actually a bad pivot choice, wasn't it? Because it was on the end over here. So what we did is we swapped 4 with 0. So now everything to the left of 4 is less than 4. We choose 0 as our pivot. Well, that's a bad choice again. Now everything to the right is there. And then we're going to sort this 2, 1, 3 with a 1, 2, 3. And notice that here, now what we end up with is all of our pivots just stay where we put them at the end of that time through. Right? So now we end up with 0, 1, 2, 3, 4, and 5. And then we would have done the same thing with the other side as well. Again, like I said, this is considered a divide and conquer algorithm. We choose our pivot. We divide into an array that's less than the pivot and an array that's greater than the pivot. And then we solve that for that subproblem as well. Okay. All right, quick sort. So this is an example of how we get into that position with the quick sort. We choose our pivot. We move through. When we have a low value that is greater than our pivot, we hold there. Okay, we initialize low to the next position after our pivot. We initialize the high index to the last position in the array. We move low to the first value that's greater than the pivot. We move the high index to the first value from the right that's less than the pivot. Notice that 1 is less than 5. 9 is greater than 5. So what we need is we need 9 to be in the right side of the array at the same time that we need 1 in the left side of the array. Well, there's a real easy way. What we can do is we can just swap those two values, right? We could just swap 1 and 9, which is what we've done here. 1 and 9 get swapped. So now we do it again. Move high. Oh, 0, less than pivot. 3 less than pivot. 8. Okay, so 8 and 0 need to get swapped, and we do that. Now we're going to keep moving low until it gets to a value that's greater than the pivot. So low will move over to this 8 spot. High will keep moving until it gets to a value that's less than the pivot. Right? That's here in this 4. Right? And then we just simply swap the pivot with the value in the high index. So now 4 and 5 get swapped. And now what we end up with is, because 4 is less than 5, we swap it over to here because the pivot was the first value in the array, right? Then what happens? 5 gets swapped with 4. Everything to the left of 5 is less than 5. Everything to the right of 5 is greater than 5. All right. Now, there is a problem with quick sort. It is, in the average case, it's an n log n algorithm because it is a divide and conquer algorithm, but it's really a divide and conquer. It's really an n log n algorithm if we're able to partition both arrays into approximately the same size. Okay, but if for some reason, let's say that constantly the pivot that we chose is constantly on one end of the array or the other. Okay, then we really end up with an array of 0 and an array of n-1, right? Which is not very good, right? Because then it basically becomes a selection sort. Right? If we constantly choose the pivot that's on one side of the array, one side of our sorted array, then we end up with a selection sort, which is, as I've said before, it was n squared. Right? Basically, the pivot divides it into one big subarray and the other empty or really small, and so basically it doesn't do anything better than what was already some of the simplest sorting algorithms. Right? But in the best case and in the average case, we consider this to be an n log n algorithm. And there are some ways that we can choose a pivot. There's what's called the middle of 3, where what you do is you look at the first value in the array, you look at the first value in the array, the middle value in the array, and the last value in the array, and you choose the median of those 3. Right? And so in that way, you know for sure that you're not going to have an array of n-1 and an array of 0, because by choosing the median of 3 values, you know for sure that at least one value is greater than the pivot you chose, and at least one value is less than the pivot you chose. So either way, you're going to have at least one value on either side, and hopefully what you end up with is at least as close as possible to n over 2 on one side and n over 2 on the other. Okay. There's some other stuff in these slides, like the heap and what's called a heap sort, binary tree. If you're really interested in different ways that data structures are used and how algorithms can be done, because there's another what's called heap sort. It's another very fast log n algorithm, and yeah, so it's just some interesting stuff. Again, it's probably beyond. It is beyond the scope of this class, and so I'm not going to go into it in too much detail. But the way that the heap sort works can be really, really interesting for those of you who are interested in algorithms and algorithm design. Okay. Let's see, what else is there anything else in here that I really wanted to specifically go over? Okay. Not bucket sort, not radix sort. I'm gonna get into all that. All right. Yeah, the rest of those sorting algorithms were really kind of beyond the scope of this course, and so I'm not going to go into them in detail. Odd number of values for which one was that, Arjun? Go back in here. For merge sort. Well, so basically what you would do is, so let's say you had 3 values, for example, that's an odd number. You would divide it into one array of size 1 and one array of size 2. And then you would merge them together back into an array of size 3. Okay. So you basically n over 2 and n over 2 minus 1. All right, so if you had 11 values, you would break it up into an array of size 6 and an array of size 5. Kind of like, if you had 6 cards and you were merging them, right? If you're merge sorting them, okay. The idea is you just kind of take the lowest from one side and the lowest from the other side, and you compare them. Make sure they're sorted already. Yeah. Okay. Take the lowest from one side and the lowest from the other side. You take the lowest one here and put it first. All right. And you take the next one in each side. Lowest one here. Put it next. Lowest one here. Put it next. Lowest one here. Put it next. Lowest one here. Oh, that one. Put it next. Lowest one here. Put it next. Okay. And that process doesn't change if instead of 6 cards, if you only had 5 cards. All right. Take that one, throw it away. So now you have, let's say, let me look at it like this, right? These are my 3 cards and 2 cards. The process stays the same. You still compare the first card to the first card, and this one's our guy. You still compare the first card to the first card. Now, because they're both equal, that one's a little bit harder, but let's just say this one here. Okay. You still compare the first card to the first card. You still compare the first card to the first card. This one. Still compare the first card to, oh, nothing. All right, over here. Okay. So the merging process doesn't change just because the 2 arrays are not the same size. Okay. All right. Good question, though. Any other questions? All right, so what we'll do then is we'll take another break since we finished that up a bit bit quicker than I thought it would go. And what we'll do is we will take a 10-minute break, and when we come back, we'll do a final exam review, and then that will be it. We'll be done with all lectures for the spring 2021 semester. All right, so I'll see you guys in 10 minutes.